Welcome back to the channel. In this video, I am going to discuss Cambridge IGCSE Physics, Paper 6, May June 2024, Paper 61. So along with the discussion in this video, I am going to give you some tips on how to identify the answer right away and how to write the exact answer for what is being asked here. Make sure that you do not skip watching. Let us get started. First question, a student investigates the stretching of a spring. Fig 1.1 shows the setup. A, the student measures and records in table 1.1 the unstretched length or L naught of the spring. He does not include the loops at the ends of the spring in the measurement. The value L naught is the length of the spring when the load L on the spring is 0 Newton. That also means that there's no load hanging to the spring. So it is just the length of the spring itself, right? We call it as original length or the initial length of the spring. So describe one technique you would use to obtain an accurate value for L naught. Draw a diagram to illustrate your answer. I actually, when this kind of question is being asked, you have to look back at the figure that they drew here. Don't you think that there is a certain distance between this spring and the middle row? So due to that distance, because it does not put on top on the scale of the meter rule. So sometimes due to the misjudge of the value, you might not be able to get an accurate value of the length of the spring. So I am going to draw a diagram to illustrate the answer because they asked us to draw. I'm going to use a ruler. Let me draw. Okay, so since they asked us to draw, then I will just draw it. This is my diagram. This is my meter rule actually. Mm, And then, okay, this is a bench. Okay, I'm gonna draw the bench here. Okay, meter rule is placed on the bench. This is a bench. Then I just keep the ruler first. Okay, this is the meter rule. And then there's the retort stand. Okay, this is the retort stand. And then this is the balls and the the clamp. Okay, so I'm gonna just go draw it like that. And then this is my spring hanging. Okay. So first of all, to make sure to obtain an accurate value of L naught, you look at the meter rule. Meter rule is drawn straight. I can see from Fig 1.1. But in the real life, when we conduct the experiment ourselves, maybe due to the surface of the bench, which is not straight, right? You could have clamped the meter rule a little bit slanted. So that is why, okay, in order to make sure the reading of L naught is as accurate as possible, I need to put this beside meter rule. So this is called set square. You know, geometry set, you have this right angle triangle, that is being called set square. So I can make sure that the meter rule is as vertical as 90 degrees, right? So it is vertical, 100% vertical, but still there is a little bit distance between the spring and the middle row. So how do we make sure that our reading is as accurate as possible? Now, I am still going to use the same thing. This is also called set square. I place the set square as a guide here. Okay, this is my set square as a guide, right? As a pointer to guide me to read the reading on the middle row. So that is how I'm going to do it. But I will not just leave my diagram like that. So I will just copy it back. This is called clamp stand. This is the spring. And then this is a meter rule. This is a bench. I added set square I just put this as 1, and then this is set square 2, right? I have 2 set square. Now, I just describe the technique by using the set square. I would just say that set square 1 is to make sure rule is vertical to the bench. Set square 2 acts as a guide to read from meter rule. You could also say that make sure the eye level is perpendicular to the scale on the meter rule to avoid parallax error, if you remember, right? Because you are the one that taking the reading. You're the one that reading the readings, right? From the meter rule, right? Anyone could do, right? Any one of these points would do. Now, B, the student suspends a load L, which is equal to 1 Newton from the spring. He records the new length L of the spring in table 1.1. He calculates the extension E of the spring using the equation E is equal to final length L minus L naught, initial length of the spring, and records the value of E, which is the extension, in table 1.1. The student repeats the procedure using loads L equal to 2 Newton, 3 Newton, 4 Newton, and 5 Newton. The readings and results are recorded in table 1.1. Calculate the extension E of the spring using the equation E equal to L minus L naught when L is equal to 5 Newton. Record this value of E in table 1.1. Now, how do you get the value of E? They have already mentioned. This is quite easy. Don't you think so? E is equal to the L, which is equal to 23.7. You just minus with L naught. What is L naught again? L naught is the initial length when there is no load on the spring, which is equal to 2.1 cm. So the answer is 21.6 cm. Just put it here. Fill in the blank here. 21.6 is the answer. Now, see, plot a graph of L, which is on the y-axis. They have been very, very clear about this. L must be on the y-axis and E must be on the x-axis. Start both axes at origin. 0, 0. Draw the best fit line. If the question mentioned that you have to start from origin, you cannot start from any other values, right? So I have plotted all the points here, L. Okay, first of all, you have to label your x and your y-axis. Right, my y-axis L/Newton. My x-axis is E/cm. And then you plot all the points, draw your best fit line. That's all. Now, determine the gradient G of the graph, and you have to show all your workings and indicate on the graph the values you use, right? So I am going to draw, okay, this is the value that I use to calculate my gradient. So you need to have 2 points. The other value that I use is this one. 0, 0, right? And then I draw my right angle triangle. Make sure that, because for a graph, for a straight line graph, if you want to determine the gradient of the graph, you have to make sure that the triangle is occupying at least half of your straight line graph. If straight line graph is this length, make sure that it occupies at least half. Don't draw your triangle very small, because that will contribute to inaccuracy in your gradient calculation. So this is my triangle. So to calculate the gradient, G is equal to y2 minus y1 divided by x2 minus x1. This is a little bit of math. So I put 5.3 minus 0 divided by 23 minus 0. So I got my 2 point here, 23 and 5.3. So the gradient value that I got was 0.23. So I just fill in the blank, 0.23. Now G is numerically equal to the spring constant K. Record the value of K to a suitable number of significant figures for this experiment. Include the unit. For gradient, on the other hand, you need not have to include the unit, because gradient is just y-axis divided by x-axis. It's just a number, right? Actually, from math, right? But since this gradient represents spring constant is one of the physical quantities you have to put in unit. Without the unit, you will lose 1 mark. So you have to remember that. When the question asks you to include the unit, just include, right? So I will teach you how to get the exact unit. Some students, they couldn't remember what is the unit of spring constant. Don't worry about that. I'm going to show you. Now, I have to show that G is equal to K. That is why K value is equal to 0.23. Now, to find the unit of K, right? Remember, how do we calculate G? Right? G is calculated from the difference between the two y-axes divided by the difference between the two x-axes. First, you look at the unit on your y-axis because you take the y-axis divided by x-axis. So the unit of the y-axis is Newton. What about the unit on x-axis? It is cm. So Newton divides cm. Therefore, the unit of gradient is Newton per cm, and the unit of K would take the same. Newton per cm. I put 0.23 Newton per cm. Remember, significant figures can be 2 to 3 significant figures. That's it. Now, question number 2, a student investigates the resistance of a wire. Fig 2.1 shows the circuit used. A, the student measures the current I in the circuit. She places the sliding contact S at a distance D is equal to 50 cm from B. She measures the potential difference PD V50 across the length D of the resistant wire. Fig 2.2 shows the ammeter and voltmeter. First one, record the readings on the ammeter and voltmeter. Include the units. Include the unit. So you have to include the unit. Now, let me look at the reading of ammeter. The difference is 0.02. Now, this is 0.3 right here, 0.32, 34, and 0.36. 0.36. Ammeter, the unit is just right here. Just put ampere. And for voltmeter, the difference is 0.2, right? The smallest scale is 0.2. This is 1.2. This is 1.4. Okay, this is 1.4. So this is 1.4 volt. That's the unit of voltmeter, right? But the voltage or the PD. Now, the second part, calculate the resistance R50 or 50 cm of the resistor wire using the equation R50 is equal to V50 over I. Include the unit. V50 is the one that we have determined earlier, which is 1.4 volt over I value, which is 0.36 ampere. And I got 3.89. If you want to put volt per ampere, yes, you are allowed to do that. Or, you know, the unit of resistance, it is ohm. You can put a unit ohm as well. Or equivalent unit, which is volt per ampere. Not a problem. Now, the third one, calculate R1, a value for the resistance per cm of the resistant wire using the equation where D is equal to 50 cm, include the unit. R1 must be per cm. So I am not going to change the D, which is already in cm to meter. R50 is equal to 3.89 ohm and divided by 50 cm. And my answer was 0.0778 ohm per cm. 0.0778 ohm per cm. That's the answer. B, the student repeats the procedure in A using D is equal to 75 cm and calculates R2 using the equation R2 is equal to R75 divided by D. A student suggests that the resistance per cm of the resistor wire is constant. Okay. Now the first part. State whether your results support these suggestion and justify your statement by reference to the result. Actually, for this part of the question, right, if you want to ask, is there any statement like if whether the mark scheme has already fixed, whether it has to be suggested, it has to support the suggestion or not supporting the suggestion. There is no correct, there's no wrong answer. It is depending on how you answer the question. Yeah, based on your own judgment as an experimenter. Now, my statement is I said yes. Okay, justification is that you need to prove it, right? From calculation, from the result that you have, why do you say yes? Why this result support the suggestion? Okay, I said because the difference between the values of R2 and R1 is equal to 0.081 ohm per cm minus 0.0778 ohm per cm is equal to 0.0032 ohm per cm. And to me, the difference is very small and within the limit of experimental accuracy. That's it. But if your statement is no, right? So you have to justify it. If you think that the difference is too large, then your answer will be the difference is too large and it is beyond the limit of experimental accuracy. That is how you're supposed to answer. Right, the second part, the student plans to plot a graph of resistance R against length D to test the suggestion. Suggest suitable additional values of length D to use, right? So if you plan to plot a graph, you need to make sure that you have a wide range, right, of the values of D value. Now, let me scroll up a little bit. This is about a student investigates the resistance of the wire, right? And then this is a resistant wire. And normally resistant wire will be placed on a meter rule, right? Normally the resistant wire, because or how do you measure the length of the wire? You're using the meter rule. Normally we just tape it on top of a meter rule. Make sure that it is as straight as possible, as tall as possible, and then you just click at two ends. Right, so I would say that suitable length would be the student has already measured 50 cm, student has already measured 75 cm as well. That is why I would suggest maybe smaller scale, 10 cm, maybe 20 cm, okay? And then to plot a graph, you need more readings in order for you to plot an accurate graph, right? 20 cm, maybe 60 cm. Sorry, I have to put, okay, 60 cm, maybe 90 cm, and to maybe maximum of 100 cm. 1, 2, 3, 4, 5, 6, 7. I have altogether 7 values because the student has already measured 75 cm and 50 cm. You can put as many values as possible. Now, C, a variable resistor is the circuit component that can be made using a coil of resistant wire. Draw the circuit symbol for a variable resistor. Variable resistor, remember, rectangle, and then with an arrow pointing up. Variable. You can vary the resistance, right? So for this part, right, part B, I would like to fill in the unit for part B. Volt is in volt. R resistance, you put in ohm. And then R1, R2, remember? R2 value, R2 unit, you just follow the unit of R1, ohm per cm. That's it. Now, question number 3, a student investigates the image produced by a lens. Fig 3.1 shows the setup. Now, Fig 3.2 shows the height h0 of the illuminated object. On Fig 3.2, measure h0. So you have to place your cm rule on h0 to measure that h0, and I got 1.6 cm. B, Fig 3.1 is drawn to scale. The actual distance u between the illuminated object and the lens is 20 cm. First part on Fig 3.1, measure the distance x. Just put your meter rule horizontally. Oh, I'm sorry, you're not using meter rule, you're using cm rule. Just put it horizontally. Yeah, between the two arrows of x. And I got 2 cm, as small as 2 cm. And calculate the scale ratio R using the equation R is equal to U over X, where U is equal to 20 cm. Now, very easy. R is equal to U is 20 cm. You just use 20 cm divided by X is 2 cm. Just put 2 cm here. That will do. And the unit must be cancelled out. I got 10. R is equal to 10 without the unit. See, the student moves the screen until a focus image is form on the screen. C.1 on Fig 3.1, measure the distance y. Again, scroll up to y. Place the cm rule horizontally. Measure the distance between two arrows where that's the value of y. I got 6.2 cm. Third, calculate the actual distance v between the lens and the screen using the equation v is equal to ry. Use your value from r from b part 2. Now v is equal to ry. R from part 2, I got 10, and then I just times 6.2 cms, and therefore I got 62 cm. 62 cm is my answer. D, calculate the focal length f of the lens using the equation f is equal to uv over u plus v. Give your answer to a suitable number of significant figures for this type of experiment. Now, let me calculate this first, and I'll give you a tip after that. F is equal to uv. I'm just copying it back. U plus v. F is equal to u. Let me check my value of u. Oh, it is 20. 20 times v, 62, divided by u plus v, 20 plus 62. My f, I got, do you know how many significant figures that you're supposed to give to your f? U and v. Look at the value of u and v. There are two significant figures. Therefore, f can be recorded as two significant figures to three significant figures. You put 15 cm, yes, not a problem. You put 15.1 is also not a problem. 2 to 3 significant figures will do. So I put 15.1. Now, E, in this type of experiment, it can be difficult to judge the screen position that produces the clearest image, which is definitely true. Suggest 2 precautions or techniques to overcome this difficulty. Actually, we can just minimize it, but not entirely overcome these difficulties. It is always very hard, right? So I think that, okay, another tips that I want to give you, if this is about this, can you see this? Illuminated object. Make sure that you conduct the experiment. It is a general precaution, right? Conduct experiment in a dark room. This is like general, right? General technique in order for you to view the image, right? Clearly. Now, sometimes when you see that sometimes it is very hard to judge which is the clearest image because, right, the image form is sometimes you think that is clearest, but sometimes you think that it's not so clear. So once you have judged, not judging, you think that that's the clearest image, you try to move your screen a little bit forward to see whether the image get blurred, right? And then go back to the position that you think that you saw the clearest image. Try to move to the back just a little bit, just to see whether it get blurred. If you move forward from the one that you think that that's the clearest image, you move forward, you get blur image, you move backward, you get blur image. That's the clearest image, the one that you judge initially. Yeah, so I'm going to talk about that. I say that move screen back and forth when the sharpest image is formed. Move the screen a little back and a little forth from the one that you have determined, yeah? And compare the clearest image. Take the one that is clearest to you, right? Now F. Fig 3.2 shows the shape of the illuminated object. The image of the object is enlarged. Draw a diagram to show the image that you will see on the screen. So this is a convex lens. If you can see this convex lens, it will form inverted image. This is what I'm seeing. Okay, it is inverted triangle. That will do. Question number 4, my favorite part. planning experiment. I feel so good to plan the experiment, right? So we are the planner. Don't you feel great? Now, let me read the question. A student investigates the bending of composite strips of wood, right? Because they stick all the woods together. When they're loaded at one end, the composite strips are made from identical layers of wood stuck together. So it's just like layer cakes like that, right? Stuck together as shown in Fig 4.1. Plan an experiment to investigate how much composite strips bend when they are loaded at one end. Fig 4.2 shows the setup the student uses. The student has a number of composite strips made with two or more layers of wood. They put a G-clamp, they put a composite strips there, and a bench there, and a floor. In your plan, state the variable that you are testing. I want to test the bending distance. Initially, the composite strip is horizontal. So whenever you place a load at the end here, you could see that it will bend, right? So I am going to add to this diagram just a little bit to make sure that you understand better. I'm going to use my ruler. Where's my ruler? I'm going to make sure that, okay, 90 degrees. I'm going to place a ruler here. Okay. Not too close because I don't want the ruler to exert frictional force to my composite strips. Here, this is my ruler. And then the other one would be my retort stand. Okay, retort stand must be higher a little bit. Okay. And I'm going to keep my ruler right now. Okay. Now this is my retort stand. Okay. Okay. Even though it looks like the scales are different from a meter rule. Okay. Okay, this is it. Okay, this is my meter rule. Must be clamped to a retort stand, and then I place a mass here, a load. Right? And then, okay, the bending part. This is very important. How did I go draw it? I tried my best. Okay. Um, it is actually like this. Okay, I better use the black color to draw it. Mm, okay, so this is called bending distance. That's my bending distance. And I have to label this is a load. This is a meter rule. This is a retort stand. So you remember how to make our meter rule vertical? You have to use a set square. So this is my set square, just to make sure that the rule is vertical, so that I could measure the bending distance as accurately as possible. Now, okay, I'll answer the question right now. Variable that you are testing, I'm testing. Variable. Is it variable? Okay, that is being tested. I just fill in the blank. Bending distance. How much the rod would bend. And then I am done with the first part. Second part, list any additional apparatus that you would use. So I'll just write that down. Additional apparatus. You saw what I drew. I use mirror rule. And then that's it. Yes. Okay. And then maybe electronic balance. Electronic balance, because I want to measure the mass of the load first. Right? And then the set square that I use because I want to make sure that the rule is vertical. Set square. I have done the second part. Explain briefly how to do the investigation. That is the method. So I am going to write down the method. Methods or procedure. So I would say that set up, because I drew something on the diagram given. So set up the apparatus. apparatus as shown. And then I would say that initial height of strip is measured by meter rule. After that, maybe I place 20-gram mass. Okay, measure a mass. Measure the mass of load using electronic balance. And then number 4, place, or I just say, okay, 20-gram mass is stick to the end of strip, right? Is this a strip? Okay, yes, it is called composite strip, okay, by using glue, because sometimes it might be falling off from the strip. So that is why I want to stick it by using glue. Now, and then after that, final height of strip is measured by meter rule. Bending distance can be calculated from difference between final height and initial height. And then number 7, or the last part, remember, always end your procedure or your method with repetition. Repeat the experiment with maybe 30 gram, 40 gram, 50 gram, 1, 2, 3, 4, 60 gram, and 80 gram masses, right? So I'm done with that method. And the next one is take the key variables to keep constant. That is the controlled variable. I'll write it down as controlled. They are all variable, the one that we can vary. It's just that during the experiment, we want to keep all these variables to be constant. I state that length of the strip remain the same. You do not increase the length of the strip, or you do not shorten the length of the strip. Or maybe diameter of a strip, diameter of strip. Remember how the strip is being made? You just stack out different numbers of wood on top of a strip, right? And make sure that initial height is the same. Initial height, maybe? Make sure that the same height, so that, right, it is easier. Now, done with that, for these key variables to keep constant, it is suggested that you write more than one, because this is variables. Variables means plural, right? Now, the next one, draw a table, right? So table, I'll just write here, my table would be mass, which is in gram, and then maybe bending distance. So I can fill in blank for my mass, because I start with 20, 30, 40, 50, 60, and 80 gram, right? And I do not fill in for my bending distance, because I'm the planner. Remember, I'm not the one that conduct the experiment, but I am the one that suggested the values of the masses. That is why I can fill it in. Now I'm done with table, and the last part, explain how to use your readings to reach a conclusion. So since I have two variables here, one is independent variable, the other one is dependence variable. Therefore, I just want to plot a graph, right? Conclusion, maybe you can say plot a graph of mass in gram against bending distance, which is in cm, okay, to see the relationship, because I really don't know. I'm just a planner because this experiment is new. Yeah, it's not being conducted yet. That is why. And yeah, that is all about the discussion for this May June 2024 paper 61. If you need the PDF solution for this paper, do not hesitate. Just make sure that you comment below. Thank you very much for watching and see you in my next video. Bye.